The patterns and practices discussed in this video are for educational purposes and are based on industry best practices. Always consider your specific architectural needs, team capabilities, and business context before implementing any solution. This isn't a silver bullet, but a map to help you navigate the complex world of system design. It's 3 in the morning. Your phone screen blasts your eyes with the cold, hard light of a PagerDuty alert. The checkout service is down. Again, your heart sinks. You stumble to your laptop, coffee already brewing, and dive into the logs. But the error message is cryptic. It's a timeout. The checkout service isn't the problem. It's just the first domino to fall. You trace the call stack. Checkout calls the payment service. The payment service is fine, but it calls the inventory service to reserve the item, and the inventory service is just hanging, waiting. You dig deeper. The inventory service is waiting on a response from the shipping service to get a real-time shipping estimate. And the shipping service? It's making a synchronous blocking call to a 20-year-old SOAP API hosted on a mainframe in a dusty server room to validate an address. That ancient system, under the load of a flash sale, has finally given up the ghost. The entire e-commerce platform is grinding to a halt because of a single, brittle, poorly designed integration point. Sound familiar? This isn't just a bad dream. This is the daily reality for countless developers trapped in what we call a distributed monolith. It's the monster we created when we chased the microservices dream without a map. We were promised speed, agility, and independent deployments. We were told we could break up the giant scary monolith into small manageable pieces. And we did. But what we ended up with, in many cases, wasn't a fleet of nimble independent services. It was a digital Frankenstein's monster. A tangled mess of dozens, sometimes hundreds, of services all talking directly to each other in a chaotic, unpredictable web. Every service knows way too much about every other service. A small change in one service causes a cascading failure across 5 others. Deployments are terrifying because you have no idea what you might break. You've traded one big ball of mud for 100 tiny balls of mud, all connected by brittle, invisible strands of string. This is the great irony of modern software development. The very tools and architectures designed to make us faster have, for many, created a new kind of complexity that is far harder to reason about and far more dangerous to operate. The problem isn't microservices. The problem isn't the cloud. The problem is that we forgot the first principles of how to make systems talk to each other reliably and effectively. We've been so focused on the what, Kubernetes, Docker, serverless, REST, gRPC, that we've completely ignored the how. How do you decouple services so they can evolve independently? How do you ensure a message sent is a message received, even when networks fail? How do you route a single request to different processors based on its content? How do you transform data from one format to another without littering your business logic with conversion code? What if I told you that the answers to all of these questions have existed for 20 years? That a complete blueprint for solving these exact problems was laid out in a book that is, to this day, one of the most important and overlooked texts in software engineering. Most of you have heard of the Gang of 4 Design Patterns book. It gave us the vocabulary for object-oriented design, singleton, factory, observer. It was revolutionary. Well, in 2003, Gregor Hope and Bobby Wolf did the exact same thing for system integration. They wrote the book, Enterprise Integration Patterns. And it is, without a doubt, the missing manual for the microservices era. This book codified a visual language and a set of 65 fundamental patterns for designing asynchronous, message-based systems. These aren't specific technologies. They're not about Kafka or RabbitMQ or AWS SQS. They are the timeless, fundamental ideas that make those technologies work. They are the architectural DNA of every robust, scalable, and resilient distributed system on the planet. Learning these patterns is like a software architect's superpower. It allows you to look at a complex mess of interconnected services and see the underlying structure, the flow of information, and the points of failure. It gives you a shared vocabulary to discuss system design with your team, moving you from vague hand-waving to precise, actionable plans. And right now, in our world of event-driven architectures, serverless functions, and globally distributed applications, these patterns are more relevant than they have ever been. They are the key to unlocking the original promise of microservices: true decoupling, independent scalability, and resilience in the face of failure. So that's what we're going to do. In this video, we are going to unpack the 5 most critical, most foundational enterprise integration patterns that you absolutely must know to build modern software. These are the ones I see used and misused every single day. These are the patterns that will fundamentally change the way you think about connecting systems. We're going to cover Number 1. The message channel, the absolute bedrock of asynchronous communication. This is the how behind decoupling your services, making them blissfully unaware of who is on the other end. It's the difference between a phone call and a post office. Number 2. The message router. Once you have messages flowing, how do you direct traffic? This pattern is the system's central nervous system, intelligently deciding where a message needs to go based on its content, without the sender ever needing to know the destination. Number 3. The message transformer. Your services speak different languages. The billing service wants XML, the new machine learning model needs JSON, and the legacy system only understands fixed-width text files. The transformer is your universal translator, keeping your core business logic clean from the messy work of data conversion. Number 4. The message endpoint. This is the unsung hero of integration. It's the adapter that connects your application code to the messaging system itself. Get this pattern right, and you can swap out your entire messaging infrastructure, say from RabbitMQ to Kafka, without changing a single line of your business logic. And number 5, the pipes and filters architecture. This is where we put it all together. It's a powerful pattern for processing a message through a series of independent, sequential steps. Think of an assembly line for your data. It's the secret behind building complex workflows that are incredibly simple to understand, test, and modify. Over the next few minutes, we're not just going to define these 5 patterns. We're going to bring them to life with real-world examples you can actually use. We'll explore the why behind each one. We'll look at the common pitfalls and anti-patterns to avoid. And by the end of this video, you will have a powerful mental toolkit that will allow you to design systems that are not just functional, but also resilient, scalable, and maintainable for years to come. You'll be able to walk into any architectural review meeting and confidently diagnose the root cause of integration problems and propose elegant, proven solutions. So, if you're tired of fighting with brittle, tightly coupled services, if you're ready to finally build systems that work with you instead of against you, then stick around. Let's start by dissecting the single most important pattern of them all: the message channel. Imagine a busy city street. On one side, you have a baker. On the other, a customer who wants a loaf of bread. In a tightly coupled world, the baker has to stop everything, run across the street, hand-deliver the bread, take the payment, and run back before they can bake the next loaf. If the customer isn't home, the baker waits. If there's a parade blocking the street, the baker waits. Nothing else gets done. This is how so many software systems are built, with direct synchronous calls. The order service calls the inventory service and waits. Then it calls the shipping service and waits. The entire process is held hostage by the slowest or least available component. A message channel is the pneumatic tube system you see at a bank drive-thru. It's the city's postal service. It's the ultimate middleman, and I mean that in the best way possible. Instead of the baker running across the street, they simply put the loaf of bread into a delivery box, slap a label on it, and put it on a conveyor belt. They can then immediately turn around and start baking the next loaf. They don't know, and more importantly, they don't care if the customer is home right now. They don't care if the delivery truck gets a flat tire. They trust the postal service, the message channel, to handle the delivery. This is the absolute core of decoupling. The sending application, our baker, only needs to know one thing: how to put a message onto the channel. The receiving application, our customer, only needs to know how to pick a message up from the channel. They never need to know about each other. They don't need to be running at the same time. They don't need to be written in the same programming language. They are completely independent. This one simple idea gives us 3 superpowers. First, asynchronicity. This is what we just described. The sender fires and forgets. When a user clicks place order on your website, your order service can create a message, a little packet of data containing the order details, and place it onto a channel called, say, orders to process. It can then immediately return a thank you page to the user. The user experience is instantaneous. They aren't stuck watching a loading spinner while your system grinds away in the background trying to talk to 5 different services. The actual work of processing the order happens behind the scenes asynchronously. Second, reliability. What happens if the shipping service, the one responsible for printing labels, goes down for maintenance? In the old world, the order would fail. The user gets an ugly error message. But with a message channel, the process shipping message just sits safely in the channel, waiting. Think of it like a letter sitting in a P.O. box. When the shipping service comes back online, it checks its inbox, sees the message, and processes it as if nothing ever happened. The channel acts as a buffer, a shock absorber for your entire architecture, making it resilient to temporary failures and outages. And third, scalability. Let's say it's Black Friday and orders are flooding in. Your single shipping service can't keep up. With a message channel, the solution is beautifully simple. You just spin up 5 more instances of the shipping service. All 5 of them can now pull messages from the same channel, working in parallel to blaze through the backlog. It's like adding more cashiers at the grocery store when the lines get long. You didn't have to change the order service at all. It's still just happily dropping messages onto the channel, completely unaware that its workload is now being handled by a whole team. Now let's get a little more specific. What is a message channel? In practice, it's a piece of software, a broker like RabbitMQ, Apache Kafka, or a cloud service like Amazon SQS or Google Pub/Sub. And the channel is just a named destination within that broker, like a queue or a topic. And the channels themselves come in 2 main flavors. This is really important. First, you have the point-to-point channel. This is exactly what it sounds like. One sender puts a message on the channel, and it is consumed by exactly one receiver. It's like a direct instruction. The order service might put a message on a deduct inventory channel. It expects one and only one inventory service to pick up that message and perform the task. If you have 5 inventory services running for scalability, they will compete to consume messages from the queue. One service gets message A, another gets message B, and so on. This ensures that each task is only performed once. This pattern is perfect for commands, for when you want to tell a specific type of component to do something. But then you have the second and arguably more powerful flavor, the publish-subscribe channel, often called pub/sub. This is not a direct instruction. It's a public announcement. It's like a town crier shouting, "Hear ye, hear ye! A new order has been placed." The sender, our order service, publishes an event message to a topic. Let's call it order placed events. It doesn't know who's listening. It doesn't care. Now, any other service in our entire ecosystem can subscribe to that topic. The shipping service subscribes because it needs to ship the order. The inventory service subscribes because it needs to update stock levels. A new analytics service subscribes because it wants to update a real-time sales dashboard. An email service subscribes to send the customer a confirmation. Do you see the magic here? The order service has no idea these other services even exist. Its only job is to publish that one event. Tomorrow, if the marketing department wants to build a new service that gives loyalty points for every order, you don't have to go back and change the order service. You just build the new loyalty service and have it subscribe to the order-placed events topic. It's infinitely extensible. This is how modern event-driven architectures are built. And the publish-subscribe message channel is the beating heart at the center of it all. So, by using message channels, we break the chains of tight coupling. We move from a brittle, synchronous house of cards to a resilient, asynchronous, and scalable system of independent components. We're no longer forcing our baker to run across the street. We've built a robust postal service. The baker bakes, the delivery service delivers, and the customer gets their bread. Everyone is focused on what they do best, and the entire city runs more efficiently. But this raises a critical new question. We've built this incredible delivery system. Our pneumatic tubes and conveyor belts are all in place. But what are we actually putting in the packages? What does the message itself look like? If the baker writes the delivery address in French, but the delivery driver only reads English, the package still isn't going to get where it needs to go. The physical connection is solved, but the communication, the language, is still a problem. How do we ensure that the data we put into a message is understood by whoever receives it, especially when they might be written by different teams in different languages a year from now? Solving that problem, the problem of the message content itself, leads us directly to our second foundational pattern, the canonical data model. If messaging is the postal service of our software architecture, the canonical data model is the decision to make English the official language of all mail that passes through it. It's the universal translator, the Rosetta Stone that allows completely different systems to have a meaningful conversation. Let's make this concrete. Imagine a modern e-commerce platform. It's not one giant application. It's a collection of specialized services. You've got an order service that takes in new orders, a shipping service that handles logistics, a billing service that processes payments, and a customer service that manages user accounts. Now, a customer places an order. The order service creates an internal record. To itself, this record is perfect. It might have fields like ord_id, cust_f, and item_list. It's optimized for its own database and its own internal logic. But now it needs to tell the shipping service to prepare a shipment. So it fires off a message. But what does the shipping service expect? The shipping service team, a completely different group of engineers, designed their system to think in terms of shipment requests. Their internal object might have fields like shipment_ID, recipient_address, and package_contents. See the problem? The order service is speaking its own dialect, and the shipping service is speaking another. They're talking about the same core concept, getting a product to a customer, but their vocabularies are completely different. Cust_f in one system is recipient_d in another. Item_list is package_contents. Without a plan, you have two terrible options. Option 1. The order service developers have to learn the specific, internal data structure of the shipping service and transform their data into that exact format. Okay, fine. But now the billing service needs to know about the order too, and its format is different again. And then the customer service needs to update the user's order history, and its format is also different. Suddenly, the order service team isn't just managing orders. They're now experts on the intimate, internal details of every other service in the company. They're maintaining a complex web of custom translators. If the shipping service team decides to refactor and rename recipient_address to delivery_location, the order service breaks. This is called tight coupling, and it is the enemy of agility. It's a distributed monolith, the worst of both worlds. Option 2 is even worse. Every service just broadcasts its own native format and expects every other service to figure out how to parse it. This is pure chaos. It's like walking into the United Nations and having every delegate shout in their own native tongue simultaneously. Nothing gets done. This is the exact problem the canonical data model is designed to solve. Instead of creating n-squared point-to-point translations, you create one shared authoritative data format for the core business concepts that flow between your services. You don't force the order service to change its internal database. You don't force the shipping service to change its internal code. You let them keep their native languages for their own internal affairs. But you get all the teams in a room, the architects, the senior engineers, the business analysts, and you have a critical discussion. You ask, what in its purest form is an order in our business? You negotiate. You design. You agree. You decide that, for the purpose of communication between services, an order will have a customer identifier, which is a string. It will have a shipping address, which is a structured object with fields like street, city, and zip code. It will have a list of line items, where each item has a SKU, a quantity, and a price. You build this model. This is your canon. It's the gold standard. It's the official shared language. Now, the process looks completely different. When the order service needs to announce a new order, it does one thing first. It takes its own internal messy ord_d, cust_f object, and translates it into the beautiful, clean canonical order format. Then, it places that single canonical message onto the message bus. The shipping service listens. It receives the canonical order. It doesn't care who sent it. It doesn't know anything about the order service's internal database. All it knows is how to speak the shared canonical language. It takes the canonical order and translates it into its own internal shipment request format. And it gets to work. The billing service does the same. So does the customer service. Each service is responsible for only two translation tasks: translating from its internal format to the canonical one, and from the canonical one back to its internal format. That's it. The web of n-squared connections is gone. It's replaced by a simple, elegant hub-and-spoke model where the canonical model is the hub. The benefits here are monumental. First, you get true decoupling. The order service team can now completely rewrite their entire service in a new programming language, switch from a SQL database to a NoSQL one, and change every single internal field name. And as long as, at the very end, it can still produce a valid canonical order message, guess what? No other service in the entire company cares. Nothing breaks. This freedom is how modern, agile companies out-innovate their competitors. They can evolve parts of their system without fear of breaking the whole. Second, you get immense clarity. The canonical model becomes a living document that defines the business. New developers can look at it and immediately understand the core data entities of the company. It forces conversations that should have happened years ago about what a customer or a product truly means to the business as a whole. But like any powerful pattern, it's not free. Creating a good canonical model is hard. It requires collaboration and compromise. It can be a political nightmare, as different departments argue that their view of a customer is the correct one. There's also a real danger of creating a bloated God model. A single massive message structure that includes every possible field for every possible use case. This must be avoided. Good canonical models are lean, focused, and versioned over time just like any other piece of software. And yes, there's a small performance cost. Every message now goes through a translation step on the way in and on the way out. But for the vast majority of enterprise applications, the milliseconds of latency this adds are an infinitesimal price to pay for the incredible gains in architectural flexibility, developer velocity, and system resilience. So now we have our first two patterns, the foundation of modern integration. We have a robust asynchronous postal service with message-oriented middleware. And we have an agreement to write all our letters in a single common language using a canonical data model. Our systems can now talk to each other reliably and understandably. We've solved the problems of transport and format. But a new, more subtle problem emerges. The order service sends its perfectly formatted canonical message out into the world. The shipping service and billing service pick it up. They do their work. But how does the order service know any of that happened? What if it needs a response? What if the billing service needs to reply and say, "Hey, this credit card was declined"? What if the entire business process from order placement to final delivery involves a dozen different messages across 5 different services, and we need to track that single customer's journey from beginning to end? We've figured out how to talk. Now we need to figure out how to have a conversation. And that brings us to our third and arguably most critical integration pattern, the correlation identifier. If the first two patterns were about building the roads and the cars for our data, this one is the GPS tracking number for every single package we ship. It's the simple, almost breathtakingly elegant idea that solves one of the most painful problems in modern distributed systems: finding a needle in a haystack of a million other needles. Let's go back to a physical world analogy first because it's just so perfect. Imagine you order a new gadget from a massive online retailer. The moment you click Confirm Purchase, a complex ballet begins. A system in a data center in Virginia confirms your payment. Another system in a warehouse in Ohio alerts a robot to go pick your item off a shelf. A third system prints a shipping label and schedules a pickup with a logistics company. That company then hands it off to a local courier for final delivery to your door. That's at least 4 different companies for different IT systems, all working together to get you your gadget. Now imagine something goes wrong. The package is delayed. You call customer service. What's the very first thing they ask for? It's not your name. It's not your address. It's your tracking number. Why? Because your name, John Smith, is useless. There are thousands of John Smiths. Your address is better, but maybe multiple packages are going there. That one unique tracking number, however, is the golden thread. It's the one piece of data that every single system, from the warehouse robot to the delivery driver scanner, knows about. With that number, the customer service agent can see the entire journey of your package in seconds. They can see it left the warehouse on Tuesday, arrived at the sorting facility in Chicago on Wednesday, but hasn't been scanned since. Boom! They know exactly where the problem is. Without that tracking number, they'd be completely lost. They'd have to call the warehouse and ask them to manually look through records for a John Smith. It would be a nightmare. It would be impossible. The correlation identifier is the tracking number for your software. In a microservices architecture, a single user click, like add to cart or book flight, doesn't just hit one service. It can trigger a chain reaction, a cascade of events that ripples across 5, 10, even 20 different services. The order service receives the request. It then sends a message to the payment service. The payment service charges the card and tells the inventory service to reserve the item. The inventory service then notifies the shipping service. This is our digital supply chain. And just like the physical one, things go wrong. A payment fails. The inventory check times out. A network glitch causes a message to get lost between services. And a user contacts support saying, "Hey, I tried to buy something, it said there was an error, but I think my card was still charged. What happened?" Now you're the developer on call. You have to figure this out. You look at the logs for the order service. You see a million requests. You look at the payment service logs. You see a million transactions. You have no idea which payment attempt belongs to which order request. You're trying to piece together a story from scattered, disconnected sentences. It's the digital equivalent of calling the warehouse and asking for John Smith's package. It's a slow, painful, and often fruitless investigation. This is where the correlation identifier changes everything. The pattern is this. When the very first service in the chain receives a request from a user, it generates a single unique ID. A GUID, a UUID, whatever you want to call it. Let's call it the correlation ID. From that moment on, every single message, every single API call, every single event that is part of that original user's request must carry that exact same correlation ID in its metadata, usually in a header. The order service gets the request, creates correlation ID 123ABC, and puts it in the header of the message it sends to the payment service. The payment service receives the message, processes the payment, and when it sends its own message to the inventory service, it copies that same header, correlation ID 123ABC. The inventory service does the same, passing it on to the shipping service. That one simple, consistent piece of data is the golden thread that ties the entire, complex, distributed transaction together. Now, when that user calls support with a problem, the scenario is completely different. The support agent can look up their initial request and find the correlation ID. They give that ID to you, the developer. You don't have to hunt through logs anymore. You go to your centralized logging or observability platform, your Splunk, your Datadog, your New Relic, and you pop that one ID into the search bar. And instantly, like magic, the entire story of that transaction appears on your screen, perfectly ordered. You see the log from the order service at 10:01 and 32 seconds AM. Success. You see the log from the payment service at 10:01 and 33 seconds AM. Success. You see the log from the inventory service at 10:01 and 34 seconds AM. Oh, an error. Failed to connect to database. You've just gone from a multi-hour investigation to a 30-second diagnosis. You found the needle in the haystack because you had a magnet. That is the power of the correlation identifier. It's not just a nice-to-have. For any system of meaningful complexity, it is an absolute necessity for sanity. It turns debugging from a black art into a science. It's the foundation of modern observability. Implementing it is surprisingly straightforward. If you're using message queues like RabbitMQ or Kafka, you add it to the message headers. If you're making direct HTTP calls between services, it goes in the HTTP headers. In fact, many modern tools like service meshes such as Istio or Linkerd can even inject and forward these IDs for you automatically, so your application code barely has to be aware of it. So we've established our services can talk using messaging. We've ensured they can publish and subscribe to information. And now, with the correlation identifier, we've given ourselves an X-ray machine to see the entire flow of a conversation through our whole system. We can track a single request from beginning to end. But what happens when two services in that chain don't speak the same dialect? What if our order service, created in 2022, represents a customer's address as a single string? 123, Main Street, Anytown, USA, 12,345. But the shipping service, a legacy system we bought from another company, expects that same address as a structured object with separate fields for street, city, state, and zip code. The order service sends its message. The shipping service receives it, and it breaks. It doesn't understand the format. The whole process grinds to a halt. We have a communication problem, but it's not about the connection. It's about the content. We need a way to translate on the fly, to ensure that every service gets the data in the exact format it expects, without forcing every other service in the system to conform to its specific needs. We need a universal translator. And that brings us to our fourth pattern, the message translator. Think of it as the ultimate diplomat, the universal translator from science fiction made real for your software. It's a dedicated component that sits between other services with one, and only one job, to convert a message from one format into another. It doesn't add any new business logic. It doesn't decide where the message should go. It simply takes an incoming piece of data, looks at the blueprint for what the next service needs, and reshapes it. It's a data blacksmith, reforging information into the perfect shape for its destination. Let's go back to our e-commerce platform. The order service fires off a big, beautiful, comprehensive order-placed message. This message is the source of truth. It has everything: the customer's ID, their full name, shipping address, billing address, the list of items with SKUs, names, prices, quantities, the subtotal, the tax, the final total, the discount code used, the payment transaction ID. It's a beast. A glorious, information-rich beast. But the inventory service? It's a simple, focused service. It lives and breathes stock levels. When it sees that order place message, it's like being handed a 700-page encyclopedia when all you wanted was the definition of a single word. It has to parse this massive object, ignore 95% of the fields, and pluck out the 2 tiny pieces of information it actually cares about: the product SKU and the quantity ordered. This is a problem. Not only is it inefficient, but it creates a dangerous coupling. If the order service team decides to rename the items field to line items, the inventory service breaks. If they change the structure of the address object, the inventory service might fail to parse the message, even though it doesn't even use the address. The inventory service is now fragile, and its fate is tied to parts of the system it has no business caring about. The same goes for the shipping service. It needs the customer's name and address, and the list of items to calculate weight. It couldn't care less about the payment transaction ID or the discount code. And the analytics service? It wants the order total, the customer's region, and the timestamp, but it needs that timestamp in a very specific ISO 8601 format to load it into its data warehouse. Everyone wants a different slice of the pie, and they all want it cut a different way. This is where the message translator pattern becomes a superstar. Instead of every service subscribing to that one giant order place message, they subscribe to channels that are made just for them. The message translator is the only thing that listens to the raw order placed event. When it receives one, it gets to work. First, it looks at the data and says, okay, who needs to know about this? It sees the inventory service. It then constructs a brand new laser-focused message called say decrement stock. This message contains only the SKU and the quantity. That's it. It's lean, mean, and purpose-built. It sends this tiny, perfect message to the inventory service. Next, it looks at the shipping service. It constructs another new message, maybe called create shipment. This one has the customer's name, address, and the item list. Sends that off. Finally, for the analytics service, it creates a record sale event. It pulls out the total price, the customer's location, and it takes the original timestamp and meticulously reformats it into the exact ISO 8601 string the data warehouse requires. It sends that message on its way. Do you see the magic that just happened? The order service is now completely decoupled from every other service. It can change its internal order place message format all day long. It can add fields, rename things, restructure it. Who is affected? Only one component in the entire system: the message translator. The inventory, shipping, and analytics services are completely insulated from the change. They continue to receive their own perfect, handcrafted messages, blissfully unaware that anything has changed upstream. This is architectural freedom. This is how you allow teams to work in parallel without stepping on each other's toes. The shipping team can now come to you and say, hey, we've updated our service. Our create shipment message now requires a package weight field. In the old world, this would be a nightmare. The shipping team would have to go negotiate with the order service team. The order service team would have to add weight calculation logic to their service, which has nothing to do with placing orders. It would be a slow, painful process involving meetings, tickets, and cross-team dependencies. In the new world, the conversation is simple. They tell the team managing the integration layer, we need a new field. The message translator is updated. It already has the list of items, so it can look up the weights, sum them up, and add the new package weight field to the create shipment message it generates. The order service is never bothered, keeps doing its one job well. The system evolves, but the change is isolated, contained, and managed in one logical place. This pattern is everywhere in modern software. If you've ever used an integration platform like MuleSoft or Zapier, you've used a message translator. Their entire purpose is to connect System A to System B by transforming data. When you set up a rule that says, when I get a new lead in Salesforce, create a new row in my Google Sheet, a message translator is doing that work, mapping Salesforce fields to Google Sheet columns. When you use an API gateway that takes a clean public-facing REST API call and transforms it into a legacy SOAP request to talk to an old backend system, that's a message translator. When an AWS Lambda function is triggered by an S3 file upload, parses the CSV file, and puts structured JSON messages onto an SQSQ, that function is acting as a message translator. But like all powerful tools, this pattern has a dark side. It comes with trade-offs you must respect. The biggest danger is creating a new monolith, an integration monolith. If you put every single translation for your entire company into one massive centralized message translator application, you've just moved the bottleneck. It becomes a single point of failure and a single point of contention. Every team wanting to change a message format has to get in line to have their little piece of the giant translator updated. It can become a complex, tangled mess of code that everyone is afraid to touch, slowing down innovation to a crawl. The solution is often to have many small, independent translators, each with a single clear responsibility. There's also a performance cost. This process isn't free. Parsing a message, creating a new one, and serializing it takes CPU cycles and memory. In a system processing thousands or millions of messages per second, that overhead can become significant. You're adding an extra hop, an extra step of latency, for every single message that flows through the system. And finally, there's the risk of losing information. In the act of creating a lean specific message for one service, the translator might discard data that another future service might find useful. Deciding what data to keep in a canonical event versus what to put in a translated downstream event is a delicate art. But despite these risks, the message translator is one of the most essential patterns for building resilient, scalable, and maintainable systems. It's the ultimate enabler of decoupling, allowing different parts of a complex system to evolve independently. It's the key to turning a cacophony of different data formats into a well-orchestrated symphony. So now we have our services communicating flawlessly. They send messages, a content-based router figures out who is interested, and a message translator ensures each recipient gets the data in the exact format they need. Seems like we've achieved integration nirvana, but we've just uncovered a new, far more subtle problem. Our simple act of placing an order has been transformed. It's no longer a single transaction. It's a process, a multi-step business workflow that unfolds over time, across the boundaries of multiple services. First, the order-placed event is published. Then the translator creates the decrement stock command. Then the inventory service processes it. Then the translator creates the create shipment command. Then the shipping service processes that. What happens if the shipping service is down for maintenance when its message arrives? What happens if the inventory service is overloaded and fails to process its message, but the shipping service succeeds? We've now got a shipment scheduled for a product that we haven't actually taken out of our inventory count. Our system's data is now inconsistent, and we have a ghost shipment. How do we manage the state of this long-running workflow? How do we handle failures in one step without corrupting the entire process? How do we ensure that an order is either fully processed across all services or fully rolled back? We need a way to coordinate these independent steps into a single, cohesive, and reliable business transaction. We need a conductor for our microservice orchestra. And that brings us to our final and perhaps most critical pattern, the Saga pattern. This isn't just another pattern. It's a fundamental shift in how we think about reliability in a world of distributed services. It's the answer to the question that has plagued architects for years. How do you maintain data consistency across multiple independent systems when the old safety net of a single, all-encompassing database transaction has been ripped away? In the old monolithic world, life was simple. You'd start a transaction, update the customer table, deduct from the inventory table, create an order record, and then commit. If any single one of those steps failed, the database itself would magically roll everything back. It was an atomic, all-or-nothing operation, guaranteed by the database's ACID properties. It was beautiful. It was safe. And in the microservices world, it is completely, utterly impossible. Imagine trying to do that with our e-commerce example. The order service would have to put a lock on a record in its own database. Then it would call the payment service, which would put a lock on a record in its database. Then it would call the inventory service, which would lock its database. And the shipping service would lock its database. What happens if two different orders are trying to lock the same resources at the same time? You get a catastrophic, system-spanning traffic jam called distributed deadlock. The entire platform grinds to a halt. It's a nightmare. It simply doesn't scale. So, we have to let go of that idea of atomic transactions. But we still need the business outcome to be atomic. We still need to guarantee that a customer is either charged and their product is reserved, or neither of those things happen. We can't just charge their card and then say, "Oops, sorry, we're out of stock." This is where the Saga comes in. A Saga redefines a transaction not as a single technical operation, but as a story, a sequence of steps, each of which is its own independent, local transaction. Here's the core idea. Instead of one big, scary, distributed transaction, a Saga is composed of a series of small, manageable local transactions. The order service commits its create order transaction to its own database. Then it passes the baton to the next service. The payment service runs its own local transaction to process the payment. Then it passes the baton, and so on. Each service does its one job, commits its work to its own private database, and then triggers the next step in the process. It's a chain reaction, a series of dominoes falling in perfect sequence. But right now you're probably screaming at the screen. What happens if a domino falls the wrong way? What if the fifth step fails after the first four have already succeeded and committed their work? And that is the absolute genius of the saga pattern. You can't go back in time. You can't uncommit those 4 previous transactions. The database won't let you. So instead of trying to rewind time, the saga moves forward to fix the problem. For every action in the saga, we define a corresponding compensating action. A compensating action is a separate transaction that semantically undoes the effect of a previous step. If the charge credit card step succeeded, its compensating action is refund credit card. If the reserve inventory step succeeded, its compensating action is release inventory. If the create order step succeeded, its compensating action is cancel order. So if our process fails on step 5, the saga manager, the conductor of our orchestra, doesn't panic. It calmly works backward, executing the compensating actions for steps 4, 3, 2, and 1. It refunds the credit card. It releases the inventory, cancels the order. By the end, even though we couldn't do a technical rollback, we've achieved a business rollback. We've restored the system to a consistent state. This is a profound concept. We are trading the immediate technical consistency of an ACID transaction for what's called eventual consistency, managed at the business logic level. Now, how do we actually implement this? There are 2 main flavors of the saga pattern: choreography and orchestration. First, let's talk about choreography. Think of a highly skilled dance troupe performing without a director on stage. Each dancer knows their moves, and they know which cue from another dancer to listen for. When the first dancer finishes their spin, the second dancer knows to begin their leap. It's a decentralized, event-driven approach. In our e-commerce example, the order service would create an order, and then publish an order-created event to a message bus. The payment service subscribed to that event, would hear it, process the payment, and then publish its own payment-processed event. The inventory service, listening for that event, would then reserve the stock and publish an inventory-reserved event. It's elegant, it's loosely coupled, and for simple workflows, it's fantastic. The services don't need to know about each other. They only need to know about the events they care about. But what happens when the dance gets complicated? What happens when a failure occurs? In a choreographed saga, if the inventory service fails, it has to publish a stock reservation failed event. Now, the payment service needs to be listening for that event too, so it knows to issue a refund. And the order service needs to listen for it, so it knows to cancel the order. Suddenly, every service needs to know about the failure events of every other service. The beautiful, simple dance becomes a tangled mess. It becomes incredibly difficult to see the entire business process, because the logic is scattered across every single participating service. This brings us to the second and often more robust approach: orchestration. In an orchestrated saga, we bring back the conductor. We have a central component, the saga orchestrator, which is responsible for telling each service what to do and when. The orchestrator is like the sheet music for your business process. When a new order comes in, it starts an instance of the order saga orchestrator. The orchestrator's code is explicit. Step 1. Call the order service to create the order. Step 2. If that succeeds, call the payment service to take payment. Step 3. If that succeeds, call the inventory service to reserve stock. The individual services are now much simpler. They don't need to know about the overall workflow. They just expose an API with commands like reserve stock and their corresponding compensating actions, like release stock. They just do what the orchestrator tells them to do. And here's the real power. If the inventory service fails in step 3, the orchestrator knows exactly what happened and where. It has the state of the entire workflow, so it simply goes to its error handling logic, which says, okay, step 3 failed. Now execute the compensating action for step 2. Call the payment service to refund the payment. Then, execute the compensating action for step 1. Call the order service to cancel the order. The logic for the entire business transaction, both the happy path and all the failure scenarios, is in one place. It's explicit, it's testable, and it's observable. You can look at the orchestrator and understand the entire flow, instead of hunting through 10 different services to piece together the choreographed dance. The Saga pattern is the backbone of modern, reliable distributed systems. It's what allows companies like Amazon and Netflix to process millions of complex transactions across thousands of microservices without the system collapsing into an inconsistent mess. But it's not a free lunch. It forces you to think hard about your business processes. What does it mean to undo shipping a package? You can't. So maybe the compensating action is to initiate a package recall with the carrier and send an apology email to the customer. You have to accept that for brief moments, your system will be in an inconsistent state. The payment might be taken before the inventory is confirmed. Designing these compensating transactions and managing for eventual consistency requires a huge amount of discipline. So there you have it. From the simple, powerful message queue to the flexible publish-subscribe model, to the intelligent routing of the message bus, the anti-corruption layer of the API gateway, and finally the resilient business-aware coordination of the Saga. These 5 patterns form the essential toolkit for any developer or architect building modern software. They are the techniques we use to tame the chaos of distributed systems, allowing us to build applications that are scalable, resilient, and adaptable to the relentless pace of change. But knowing the patterns is only half the battle. Knowing the ingredients doesn't make you a Michelin star chef. The real art lies in knowing which pattern to use and when. How do you decide between a simple point-to-point queue and a full-blown pub/subsystem? When does a simple workflow become complex enough to justify the overhead of a Saga orchestrator? And how do these patterns fit together to form a cohesive, elegant architecture? That is the next level of mastery, and that's exactly where we're going next. So let's dive right into that question. When does a workflow justify a Saga? The answer isn't a number. It's not after 3 microservices, or when you have 5 database calls. The answer is a feeling. It's the moment you look at a flowchart of your process and realize a simple failure could bring the whole thing crashing down, leaving your data in a state of absolute chaos. It's the moment you realize you're not just calling services, you're conducting an orchestra, and without a conductor, all you have is noise. Let's make this real. Imagine our e-commerce checkout. A customer clicks place order. In a monolith, this might be one big, happy database transaction. Easy. But in a modern distributed system, that single click triggers a cascade. First, the order service creates an order record and marks it as pending. Then it needs to talk to the payment service. The payment service charges the customer's credit card. If that succeeds, we then need to talk to the inventory service to reserve the items. If that succeeds, we talk to the shipping service to create a shipment label. Only then, after all 4 services have done their part, is the order truly confirmed. Now, what happens if the payment goes through, the inventory is reserved, but the third-party shipping API is down? The shipping service fails. In a simple, naive implementation, you're now in a terrible state. You've taken the customer's money, you've pulled items from stock that you can't ship, and the order is stuck in limbo. The customer is confused, your inventory count is wrong, and your support team is about to have a very bad day. This is the exact moment a Saga orchestrator becomes not just a good idea, but a necessity. The Saga is the conductor. It doesn't process payments or reserve inventory itself. It directs the other services. It says, order service, create a pending order. When that's done, it says, payment service, charge this card for this amount. If that succeeds, it says, inventory service, reserve these items. But crucially, the Saga knows the reverse of every step. It knows that if the inventory service fails, it must tell the payment service to issue a refund. And it must tell the order service to cancel the order. This is the compensation logic we talked about. It ensures that the transaction as a whole either completes successfully, or it is rolled back completely, leaving the system in a consistent state. It's the adult in the room cleaning up the mess. So, the Saga is managing the long-running business process. It's the brain sending out commands and reacting to outcomes. But this introduces a fascinating new problem. The user who clicked place order is still staring at a loading spinner on their screen. The Saga is busy coordinating all these services, which might take a few seconds. How do we give that user a clean, simple "your order is confirmed" message? We can't just wait for the Saga to finish. That would be a slow, clunky user experience. More importantly, the front-end application shouldn't have to know about all the individual steps. It shouldn't have to pull the payment service, then the inventory service, then the shipping service. That would be a nightmare to code and a brittle mess to maintain. It would tightly couple our user interface to our backend chaos. What we need is a way to gather up all the individual success signals from each service and combine them into one final definitive signal. We need a component that can listen to the noise of the orchestra and wait for the final crescendo before telling the audience the performance is over. This brings us to our fifth and final core integration pattern, the aggregator. The aggregator is one of a family of patterns called message routers, but it's so important and so powerful in modern systems that it deserves its own spotlight. Its job is simple in concept but profound in its impact. The aggregator collects a sequence of related messages and combines them into a single, complete message. Think of it like a journalist assembling a breaking news story. They get an initial report from a source on the scene. Then they get a confirmation from the police department. Then they get an official statement from the mayor's office. They don't publish 3 separate, incomplete articles. They wait. They aggregate the pieces of information until they have a complete, verified story. Only then do they publish the final article. In our system, the aggregator is that journalist. When the payment service successfully charges the card, it publishes an event like payment succeeded. When the inventory service reserves the items, it publishes an inventory reserved event. When the shipping service creates a label, it publishes a shipment created event. All of these events are flying around our message bus. They all contain a common piece of information, a correlation ID, which in our case is the order ID. The aggregator subscribes to all of these event types. It sees the payment succeeded event for order 123 and holds on to it. It sees the inventory reserved event for order 123 and holds on to that. It has a completion condition, a rule that says, I am not done until I have seen a payment, an inventory, and a shipping event for the same order ID. Once it receives that final shipment created event for order 123, the condition is met. The story is complete. The aggregator then does its magic. It consumes those 3 individual events and publishes one, brand new, high-value event, order confirmed. And that is the signal our front-end application or a notification service is waiting for. It doesn't care about the messy details of payment processing or inventory logic. It subscribes to one clean, simple event. When it sees order confirmed for order 123, it changes the loading spinner to a green checkmark. It sends a confirmation email. It triggers a push notification. The complexity is hidden, managed, and resolved beautifully in the back end. Now let's take a step back and look at the masterpiece we've just architected. See how these patterns aren't just isolated tools, but interlocking gears in a powerful machine. A user action triggers a command, which is sent to a message queue. This decouples the initial request from the processing, providing resilience and scalability. A Saga orchestrator consumes that command. It's the long-running process manager, the conductor, ensuring that our complex, multi-step business transaction is executed safely and reliably across different microservices. The Saga sends commands to individual services, which then do their work and publish events using a publish/subscribe pattern. This allows services to broadcast what they've done without needing to know who, if anyone, is listening. This is maximum decoupling. The payment service doesn't know or care about the inventory service, or a dozen other services that might be interested in its success. And finally, our aggregator is a specialized subscriber. It listens to this stream of events, patiently collecting the pieces of a puzzle identified by a correlation ID. Once it has all the pieces, it completes the puzzle and publishes the final picture. A single composite event that signifies the end of the business process. This is the elegance. This is the architecture. It's a system where components are independent yet collaborative. They are specialists, each doing one thing well. The Saga is a specialist in process orchestration. The services are specialists in their business domain. The message bus is a specialist in communication. And the aggregator is a specialist in message correlation and completion. By combining these patterns, we've built a system that is not only powerful but also resilient, scalable, and maintainable. If the shipping service team wants to deploy a new version, they can do so without affecting the payment service. If we suddenly get a massive influx of orders, the message queue can absorb the spike, allowing our services to process them at a sustainable pace. If a service fails mid-process, the Saga ensures the entire transaction is rolled back cleanly. And throughout it all, the user experience is kept clean and simple, abstracted away from the necessary chaos of the back end. This is the promise of modern software architecture. It's not about just making things work. It's about building systems that can evolve, that can withstand failure, and that can scale to meet demand. But as we celebrate this elegant design, a new, very practical problem emerges. The payment succeeded event might contain a transaction ID and an amount. The inventory reserved event might contain an array of SKUs. The shipment created event might have a tracking number. These are all different data structures, different formats, different languages. Our aggregator is great at knowing when the process is complete, but what should the final order confirmed event actually look like? How do we take these disparate pieces of data and transform them into a single, cohesive, and useful message that the rest of the system can easily understand? What happens when these services don't speak the same language? When one system's success is another system's gibberish? That is the messy, everyday reality of integration, and solving it is what separates the pros from the amateurs. And the key to solving it lies in our fourth enterprise integration pattern, the message translator. Think of it as the universal translator from Star Trek. You have two different species, two different cultures, speaking entirely different languages. Without a translator, communication is impossible. It's just noise. In software, your order management system speaking modern JSON, and your 30-year-old warehouse mainframe speaking a cryptic version of XML are those two different species. They have a shared goal, to get a product to a customer, but they can't understand each other's words. The message translator is that brilliant engineering officer who steps in and bridges the gap. It's a dedicated component whose one and only job is to take a message in one format and transform it into another, without altering the fundamental meaning. The most perfect real-world analogy is the humble power adapter you use when you travel. Imagine you land in Europe with your American laptop. Your laptop's plug is a Type A with two flat vertical prongs. The wall socket is a Type F with two round pins. They are fundamentally incompatible. You can't just jam your plug into the wall and hope for the best. You'll get no power and you might even break something. What do? You use an adapter. The adapter is the message translator. It has a female end that accepts your American plug, and a male end that fits perfectly into the European socket. Notice what the adapter doesn't do. It doesn't change the electricity itself. It's still 230 volts. It doesn't change the function of your laptop. It simply changes the form of the connection. It translates the physical format of the plug. This is precisely what a message translator does in our software architecture. It doesn't change the core business data, the order ID, the customer name, the product SKU, it just repackages it. It changes the message's structure, its syntax, its plug type, so that the receiving system can understand it. Let's make this concrete. Our shiny new microservice-based e-commerce platform creates an order. It generates a beautiful, clean JSON message. It looks something like this: an object with keys like order ID, timestamp, customer details, which is a nested object containing first name and last name, and an items array, where each item is an object with a SKU and quantity. It's modern, it's easy to read. It's what every developer wants to work with. It sends this message to the message broker, destined for the warehouse. But the warehouse system? It was built when the internet was still a novelty. It doesn't speak JSON. It expects a rigid, unforgiving XML format. It needs a root element called order request, with child elements like order ID, cust info with attributes for fname and lname, and a series of line item elements with product code and quantity attributes. The formats are completely different. The field names are different. Order ID versus order ID. The structure is different, nested JSON objects versus XML elements and attributes. The data types might even be represented differently. This is where the message translator component comes in. It could be a small, dedicated microservice, a serverless function, or a module within an integration platform. It subscribes to the order topic on the message broker. When it receives the JSON message from the e-commerce platform, it gets to work. Its code is a mapping exercise. It parses the incoming JSON. It reads the value of the order ID field and creates a new XML element called order ID with that value. It dives into the customer details object, pulls out first name, and puts it into the fname attribute of the cust info element. It iterates through the items array in the JSON, and for each item, it creates a new line item XML element, mapping the SKU to the product code attribute and quantity to the quantity attribute. Once it has constructed this brand new XML document, it publishes it to a different topic or queue, one that the old warehouse system is listening to. The warehouse system receives a message in the exact format it expects. It has no idea that the message started its life as JSON. It doesn't know or care that it came from a modern microservice. It just gets the data it needs in the language it understands and begins the process of picking and packing the items. Now you might be thinking, okay, I get it, but why is this a pattern? Couldn't I just write that translation code directly inside my e-commerce service? And you could, but that would be a catastrophic mistake, and understanding why is the key to appreciating the genius of this pattern. First, and most importantly, decoupling. By creating a separate translator component, you decouple the sender from the receiver. Your modern e-commerce service now has zero knowledge of the warehouse's ancient XML requirements. It just speaks its native language, JSON. It doesn't have to be polluted with ugly XML generation libraries and complex mapping logic. It stays clean, focused, and modern. This is a massive win. If down the road you finally replace that old warehouse system with a new one that also speaks JSON, what do you have to change in your e-commerce service? Absolutely nothing. You just retire the translator. The core business logic remains untouched. Second, single responsibility and maintainability. The translator has one job and one job only: translate messages between two specific formats. That's it. When there's a problem with the data format going to the warehouse, you know exactly where to look. The logic isn't buried in a 10,000-line business logic service. It's isolated in a small, well-defined component. This makes debugging 100 times easier. It makes the system easier to understand for new developers joining the team. They see a box on the architecture diagram labeled Order JSON to XML Translator, and they instantly know what it does. Third, reusability. What if another system, say a customer service portal, also needs to send information to that old warehouse system? Instead of rewriting the translation logic, it can also send its standard JSON message to the same translator, which can be designed to handle multiple inputs if necessary. You've created a reusable asset for communicating with that legacy system. The message translator is the unsung hero of many large enterprises. It's the diplomat, the interpreter, the quiet worker in the background that allows the old world and the new world to coexist peacefully. It takes the chaos of incompatible formats and imposes order, ensuring that data flows smoothly, even when the systems at either end are from different technological generations. So we've solved the language problem. The format is correct. The warehouse system can now parse the message. But as it starts to process the order, it hits a new snag. To properly route the package in the warehouse, it needs a piece of information called a bin location code. This code is based on the customer's zip code and the item size and weight. But our original order message doesn't have that. The e-commerce service has no concept of internal warehouse logistics like bin locations. All it has is the customer's address. So the message, even though it's in the right format, is incomplete. It's missing a critical piece of data that the receiving system needs to do its job. The sender doesn't have the data, and it shouldn't have the data. It's not its responsibility, but the receiver absolutely requires it. The data exists somewhere else, maybe in a separate database or another service that can calculate it. So how do we solve this? How do we enrich the message in transit, adding the missing information before it reaches its final destination, without forcing our source system to know about details it shouldn't care about? The answer is an elegant and powerful pattern, one that acts like a secret agent operating in the shadows between your services. It's our fourth major pattern, the content enricher. Think of it like this. You're sending a package, but you only have the recipient's name. You hand it off to a special kind of courier. This courier doesn't just transport the package. It first looks up the recipient's full address in a directory, writes it clearly on the box, and then sends it on its way to the central post office. The original sender, you didn't need to know the address. The final destination, the post office, didn't have to do the lookup. A specialized component in the middle handled it. That's the content enricher. In our software world, the content enricher is a component that intercepts a message, inspects its contents, and then uses information within that message to retrieve additional data from an external source. It then merges this new data into the message before passing it along to the next step in the process. Let's make this crystal clear with our e-commerce example. The order service fires off a message that looks something like this: a simple JSON object containing an order_ID, a customer_ID, and a list of product_IDs. The message is destined for the shipping service. But remember, the shipping service needs the product's weight and dimensions to calculate shipping costs. Without an enricher, the shipping service would get this message and say, okay, I have a product on 23. Now what? It would then have to make its own separate call to the product catalog service. Hey, product catalog, can you tell me the weight and dimensions for XL123? Then it would wait for a response before it could finally do its job. Now multiply that by 1,000 orders a minute. The shipping service becomes incredibly chatty, constantly making requests, and its performance becomes tightly coupled to the performance of the product catalog. This is where the content enricher steps in and changes the game. It sits between the order service and the shipping service. When the original simple order message arrives, the enricher springs into action. First, it reads the message and extracts the key it needs, in this case the product_ID. Second, it makes a targeted, synchronous call to the product catalog service, asking specifically for the weight and dimensions associated with that product_ID. Third, the product catalog service responds with the data, say, weight, 2.5 pounds, dimensions, 10 by 8 by 4 inches. Finally, the enricher takes this new information and adds it to the original message. The message that leaves the enricher is now a super message. It contains the original order_ID and product_ID, but now it also contains the weight and dimensions. When this enriched message arrives at the shipping service, its life is easy. It has everything it needs in a single self-contained package. No extra lookups, no waiting for other services. It can instantly calculate the shipping cost and move on. The beauty of this pattern is the profound decoupling it creates. The order service remains blissfully ignorant. It doesn't need to know that shipping requires weight, or that weight is stored in a completely different database. Its only job is to announce that an order was placed. It's a perfect example of the single responsibility principle. Likewise, the shipping service is simplified. It declares, to do my job I need A, B, and C. The integration layer guarantees that any message arriving at its doorstep will contain A, B, and C. It doesn't care how that data got there. This makes the shipping service easier to develop, easier to test, and more resilient. This pattern is everywhere in modern systems. Think about a fraud detection service. A payment attempted event might just contain a customer ID and a transaction amount. An enricher can intercept this, use the customer ID to look up the customer's location, transaction history, and account age from other services, and then forward this much richer payload to the fraud detection engine. The fraud engine now has the full context to make a much more intelligent decision. But like all powerful tools, the content enricher comes with its own set of warnings and trade-offs. It's not a magic bullet. The most significant risk is performance. The enricher introduces a blocking, synchronous call right in the middle of your asynchronous message flow. For every single message that passes through, the enricher has to stop, make a network request to another service, and wait for the response. If that external data source, like our product catalog, is slow or unavailable, your entire message pipeline grinds to a halt. The enricher becomes a central bottleneck. How do you mitigate this? Caching. Aggressive caching. If the enricher needs product dimensions, and those dimensions rarely change, it can cache the results from the product catalog. The first time a message for product XL123 comes through, it makes the call and stores the result. For the next 10,000 messages for that same product, it pulls the data directly from its local cache in microseconds, avoiding the network call entirely. This is a critical optimization for high-throughput systems. Another major consideration is data consistency. What happens if the enricher's cache is stale? Let's say the price of a product changes in the main database, but the enricher has an old price in its cache. It could then inject outdated information into the message, causing all sorts of downstream problems, from incorrect invoices to shipping the wrong item. You need a smart cache and validation strategy to ensure the enriched data is fresh enough for your business requirements. And finally, you have to think about error handling. What happens if the enricher tries to look up data and the external service returns an error, or simply can't find the requested information? Does the enricher drop the entire message on the floor? Does it forward the message anyway, but without the extra data? Or does it move the message to a special dead letter queue for manual inspection? The right answer depends entirely on your system's needs. If the enriched data is absolutely critical for the downstream service to function, then forwarding an incomplete message is useless. It's better to fail fast and flag the problem. But if the data is just nice to have, maybe you let the message proceed. You have to make a conscious design decision. Despite these challenges, the content enricher is an indispensable pattern. It promotes clean, decoupled services by centralizing the logic of data augmentation. It allows source systems to be simple and focused, and destination systems to receive complete, ready-to-use information. It's the unsung hero that ensures messages arrive not just on time, but with all the context they need to be truly useful. So we've seen how to route messages, how to split them up, how to aggregate them back together, and now how to enrich them with more data. We're building a powerful toolkit. But there's one final massive challenge we face constantly. Our systems rarely speak the same language. The order service might call it a customer_ID, but the legacy billing system calls it a client_reference_number. The shipping service expects addresses in one format, but the user profile service stores them in another. The data is there, the intent is there, but the formats, the schemas, the very words are different. It's like trying to connect a USB-C cable to a lightning port. You can't just jam them together. You need an adapter. So how do we translate messages between these different formats in flight, without forcing every service to become a polyglot, aware of every other system's quirks and dialects? The answer is our first and perhaps most fundamental pattern, the message translator. Think of it as a universal power adapter for your software. The message translator is a component that sits between two systems and converts messages from one format to another. The sending application fires off its message in its native tongue, say a clunky old-school XML format. The translator catches it, works its magic, and re-emits a clean modern JSON message that the receiving microservice can understand perfectly. Neither the sender nor the receiver has to change. They remain blissfully ignorant of each other's internal data structures. The legacy system doesn't need a costly rewrite to speak JSON, and the new service doesn't need to be polluted with code to parse ancient XML. This single pattern decouples systems at the data format level, allowing them to evolve independently. It's the unsung hero that keeps the peace in a diverse architectural family. Okay, so now our systems can talk to each other. But what happens when a message arrives, and it needs to go to different places based on what's inside it? An order over $1,000 might need special fraud checking, while a standard order just goes straight to fulfillment. Do we make the sending application responsible for knowing all these business rules? Absolutely not. That would create a nightmare of coupling. This is where our second pattern comes in, the content-based router. Imagine a smart mail sorter at the post office. It doesn't just look at the destination city. It might inspect the package for a fragile sticker or check its weight. Based on this content, it sends the package down a specific conveyor belt. The content-based router does exactly this for our messages. It's a central decision point that examines the message content, a field, a header, a value, and routes it to the correct channel or service based on a set of rules. An order message comes in. The router inspects the order total field. Is it greater than $10,000? If yes, it routes a copy to the high-value order queue for manual review. Is the shipping method field set to overnight? If yes, it routes it to the expedited fulfillment service. Otherwise, it goes to the standard processing queue. The router becomes the traffic cop of your system, directing messages based on their intrinsic properties, keeping the routing logic in one place, and letting the other services focus on their specific jobs. But this creates a new problem. What if to fulfill one request, we need to get information from multiple services and combine it? Think about booking a vacation package online. You need a flight, a hotel, and a rental car. Your application can't just show the user a price for the flight and say, "Hang on, we're waiting for the hotel." You need to query all three services, get all three responses, and then present a single combined package to the user. This calls for our third pattern, the aggregator. The aggregator is like a project manager for a complex request. It breaks the initial request down and sends out smaller, individual requests to multiple services in parallel. Then it waits. As each service sends back its response, the flight price, the hotel rate, the car rental cost, the aggregator collects them. It keeps track of which pieces it has and which are still missing, often using a special correlation ID to match the responses to the original request. Once it has received all the necessary responses, it combines or aggregates them into a single complete message and sends that back to the original caller. It's the pattern that turns a chaotic chorus of asynchronous replies into a single harmonious symphony of data. Now let's flip that on its head. Sometimes you don't need to combine many small messages into one. You need to break one massive message into many smaller ones. Imagine you receive a single giant order file from a corporate client at the end of the day. It contains 10,000 individual line items. Trying to process this one monolithic message could choke your system, consuming all its memory and blocking other requests. Enter our fourth pattern, The splitter. The splitter does exactly what its name implies. It takes a single large message and breaks it down into a series of smaller, individual messages. That one giant order file with 10,000 items becomes 10,000 separate messages, each for a single item. These smaller messages can then be processed one by one, or even better, in parallel by multiple instances of a service. This dramatically improves performance and scalability. Instead of one giant logjam, you have a smooth, fast-flowing river of data. The splitter is the key to achieving high throughput and resilience when dealing with bulk data. So we can translate, route, aggregate, and split. We have the building blocks for a sophisticated system. But now we come to the final boss of distributed systems, the transaction. In a single database, if you need to update two tables, you can wrap it in a transaction. Either both updates succeed or they both fail. The database is always consistent. But what happens when your transaction involves updating 3 different microservices, each with its own database? You can't just use a simple database transaction anymore. This is one of the hardest problems in modern architecture. And the solution is our 5th and most powerful pattern, the saga. A saga is a way to manage data consistency across multiple services in a distributed transaction without using locking. It's a sequence of local transactions. Each transaction updates the database in a single service, and then publishes a message or event that triggers the next local transaction in the next service. Here's the critical part. For every step in the saga, there must be a corresponding compensating action that can be run to undo it. Let's use an e-commerce order. Step 1. The order service saves a new order with a pending status. Step 2. It tells the payment service to charge the customer's credit card. Step 3. After payment succeeds, it tells the inventory service to reserve the product. If all of that works, the saga is complete. But what if the inventory service fails because the item is out of stock? The saga must roll back. The inventory service reports its failure. The order service, acting as the coordinator, then executes the compensating action for the previous step. It tells the payment service to refund the credit card charge. Once that's done, it executes its own compensating action by marking the order as failed. The system returns to a consistent state, even though a full transaction never completed. It's like a carefully choreographed dance where every forward step has a matching backward step, ensuring the floor is never left in a messy state. The saga pattern is the key to building resilient, fault-tolerant applications that can handle the inherent uncertainty of the distributed world. So there you have it. The message translator, the content-based router, the aggregator, the splitter, and the saga. These 5 patterns are not just abstract theories. They are the fundamental DNA of modern, scalable software. They are the design principles that power everything from your Amazon order to your Netflix stream. Understanding these patterns is what separates a coder from an architect. It's about moving beyond writing lines of code to designing systems that breathe, adapt, and scale. It's about learning the language of how massive, complex applications are built and maintained. When you see a system, you no longer just see services and databases. You see the flow, the choreography, the intelligent patterns that connect everything into a coherent, resilient whole. This is just scratching the surface, of course. Each of these patterns has its own deep well of strategies and variations. If you want a full, deep dive video on any one of these, especially the incredibly powerful saga pattern, you have to let me know in the comments. Which pattern resonated with you the most? Tell me below. And if this video gets to 10,000 likes, I promise I will build a complete order processing system from scratch using the saga pattern right here on this channel. So hit that like button, subscribe so you don't miss it, and thank you for watching.